a place where all the laws of science fail. Today, we take you to the darkest mystery of the universe, where time has no meaning, where space sinks into an endless abyss, and where, once you enter, no one knows what happens next. This is the story of the cosmic giants that swallow stars, dictate the fate of planets, and shape the very fabric of the cosmos. This is the story of those enigmatic entities that hold some of the greatest secrets of creation. But the real question is, could such a monstrous entity be lurking within the darkness of our own galaxy? And if it is, will we ever be able to escape its grasp? So, get ready, because we are about to step into a world where the boundaries of science blur and the truth might be more terrifying than fiction. Picture me as a whirlpool in an unfathomable ocean, not just pulling in water, but also light, time, and even space itself into my depths. No matter how hard you try to swim away, no matter how much force you exert, once you cross my boundary, no power in the universe can bring you back. This is not just gravity. This is the most mysterious trap in the cosmos, one from which escape is impossible. A black hole, a region of space where gravity is so intense that nothing, not even light, can escape its pull. Did you know that the term black hole was first coined in 1967 by American physicist John Wheeler? Before that, the concept existed, but it had no definitive name. Wheeler's words sent ripples through the scientific community, as if someone had set foot on an uncharted planet for the first time. This was not just a term, it was a gateway, a window through which we began to glimpse the deepest secrets of the universe. Sometimes, the right words can immortalize an idea, and black hole was one such term that brought it recognition across the world. But despite its name, a black hole is not entirely black. In fact, it can be one of the brightest objects in the universe. When a star falls into its gravitational grasp, its final cries echo as intense radiation that spreads across space. We see matter plunging into a black hole. But this is not merely an end, it is the beginning of a new story. Sometimes, these cosmic monsters unleash powerful jets of energy that stretch across millions of light years. This paradox is as astonishing as it is perplexing. How can something that devours even light be among the brightest things in the cosmos? The first attempt to understand gravity's mystery was made by Newton. He described it as an invisible force, a mystical rope tying Earth to the sun. A simple yet revolutionary idea. Then came Einstein, who redefined our understanding. He revealed that this rope is not an external force, it is the warping of space and time itself. Imagine placing a heavy ball on a rubber sheet, the surrounding fabric bends, and anything nearby naturally falls toward it. This is exactly what happens in the universe, where a black hole is that massive ball, warping space-time so dramatically that nothing, not even light, can escape its pull. This is not just science. This is one of the most thrilling sagas of the universe, a story still being written. Imagine standing at the edge of a towering cliff, looking down into an abyss from which there is no return. The more you lean forward, the stronger the pull into the depths feels. This very sensation is the true nature of gravity, as explained by Einstein in his theory of relativity. Newton believed that gravity was an invisible force, but Einstein completely changed this idea. He revealed that any mass distorts the space-time around it, just like a heavy ball placed on a rubber sheet bends its surface, causing everything around it to slide inward. But we cannot see this with our eyes, because it exists in a four-dimensional structure, while our world is limited to 3 dimensions. If we imagine Earth as a marble placed at the edge of an invisible valley, it would continue to roll along that slope, just like a spinning roulette ball. But the story of black holes goes even deeper. This is not just the strength of gravity. It is the ultimate fate of the most mysterious phenomena in the universe. It begins with the life of a star, a radiant, burning celestial body that sustains itself by burning fuel within. But every star has a predetermined destiny. When its fuel is exhausted, the invisible grip of gravity takes over. The star loses its balance. And just like a collapsing building crumbles into its own ruins, the star begins to collapse into itself. As it becomes denser and denser, its gravitational pull grows so intense that no force can stop it. It continues to shrink until it reaches a point from which there is no return. This point is a black hole. But this is not the end of the story, it is just the beginning. This process reaches its ultimate stage at a location that scientists call singularity, a point where density becomes infinite and the laws of physics break down. This is the place where time stands still, where concepts like here and there lose meaning. It is where everything, matter, energy, even light itself, collapses into a single direction, the unknown. This is the very heart of a black hole, where everything is lost and nothing ever comes back. Even our mathematical equations fail to define it properly, because when a calculation results in infinity, it signifies that our understanding has reached its limit. Singularity is a puzzle, a gateway that could lead to another reality, or perhaps just into darkness. It remains one of the greatest mysteries of the universe, a question we have yet to answer. But when humans first gazed at the stars, they too believed that those celestial bodies were beyond reach. Maybe one day, we will unravel the enigma of black holes too. The 1920s brought about a scientific revolution. The rise of quantum mechanics made scientists believe they had discovered a new force, one that could prevent black holes from forming. This idea was rooted in a simple yet profound principle, Pauli's exclusion principle. This principle states that no two electrons can exist in the same space at the same time. It is the reason why solid objects retain their shape and do not suddenly collapse. But this principle led to another fascinating question. When a star enters the final stages of its life, it begins to contract under the force of gravity. As the star shrinks, its electrons are forced closer and closer together. However, Pauli's principle prevents them from occupying the same space, and this resistance generates an invisible force and opposing pressure that can halt gravitational collapse. This discovery led scientists toward a new possibility. Imagine a star so incredibly dense, yet one that does not collapse into a black hole. This new type of star was called a white dwarf. A white dwarf was an unusual celestial body, small in size, comparable to Earth, yet containing the mass of the Sunday. It was extraordinarily dense, but somehow managed to avoid becoming a black hole. Scientists believed they had finally unraveled the fate of dying stars. But the most intriguing twist in this story came in 1930, when a mere 19-year-old Indian scientist, Subramaniam Chandrasekhar, approached this problem with a fresh perspective. During his journey to England, as his ship passed through the Suez Canal, Chandrasekhar was deeply engrossed in his research. At that time, scientists believed that once a star exhausted its fuel, it would shrink into a white dwarf. However, Chandrasekhar realized that they had overlooked a crucial factor, Einstein's theory of special relativity. According to Einstein's theory, as a star contracts, its electrons begin moving at extremely high speeds. But no particle can travel faster than the speed of light. This meant that if the star's mass was too great, the electrons would fail to generate the resistance needed to counteract gravitational collapse. Chandrasekhar calculated that if a star's mass exceeded 1.4 times the mass of the Sun, it could not remain a white dwarf. Instead, its collapse would continue until it ultimately transformed into either a neutron star or a black hole. This discovery sent shockwaves through the field of astrophysics. This limit, now known as the Chandrasekhar limit, determines which stars will stabilize as white dwarfs and which ones will continue collapsing, eventually becoming the most mysterious objects in the universe. The story of black holes was no longer just a convergence of gravity and quantum physics. It became a tale of courage, curiosity, and the relentless pursuit of knowledge by young scientists who unlocked the fate of the stars. Just a few years later, the story of the universe's most enigmatic objects took another dramatic turn. Scientists discovered neutrons, leading to a groundbreaking question. Could a star collapse into a dense object composed entirely of neutrons? The answer was yes. If a star was heavier than the Chandrasekhar limit, its gravitational pull would become so intense that electrons and protons would merge to form neutrons. This led to the birth of one of the densest and most mysterious stars in the cosmos, the neutron star. Neutron stars are small but astonishingly heavy. They can be as small as Mount Everest, yet contain the same mass as our Sun. Imagine this. Just a single teaspoon of neutron star material would weigh as much as all of humanity combined. This represents one of the most extreme conditions in the universe, where nature enforces its most rigid laws. But the story does not end here. If a star has a mass 2.5 to 3 times that of the Sun, even neutrons can no longer withstand the force of gravity. They are pulled even closer together, and eventually their resistance also collapses. This is the moment when contraction becomes unstoppable. No force in the universe can halt it. The star begins to sink into its own depths until it transforms into the most mysterious object in the cosmos, a black hole. This was not just a theoretical calculation, it was a solid reality of the universe. A place where the laws of physics break down, where time loses its meaning, and where nothing, not even light, can escape once it has fallen in. In the 1930s, when the scientific world was still experimenting with these ideas, Robert Oppenheimer introduced a new hypothesis about gravitational collapse. This was the same Oppenheimer who would later become known as the father of the atomic bomb. He explained that when a massive star reaches its final stage, it begins to shrink like a cloud of dust collapsing in on itself. As it becomes smaller and denser, its gravitational field grows immensely powerful. A point comes when even light cannot escape from it. This final boundary is what scientists call the event horizon. The event horizon, the invisible doorway beyond which nothing can return. This is the moment when time stops, where space-time disappears into an endless abyss. Once something crosses this boundary, it is lost to the universe forever. This idea was as terrifying as it was exhilarating. Black holes were no longer just mathematical constructs. They were real, the most unknown and most powerful objects in the cosmos. Scientists once believed that black holes were just mathematical fictions, ideas trapped in equations, concepts that could never be observed. But slowly, the mystery began to unravel. The discovery of Chandrasekhar's limit, the existence of neutron stars, and our understanding of gravitational collapse proved that black holes were not just on paper, they were out there in the real universe. The birth of a black hole is entirely dependent on Einstein's theory of relativity. As a dying star approaches the brink of becoming a black hole, its gravitational force becomes so intense that even time itself slows down. An external observer would see the star shrinking, nearing the edge of the event horizon, but appearing as if it would never quite reach it. But for someone falling with the star, the experience would be entirely different. For them, the journey to the event horizon would be almost instantaneous. The moment they cross it, every law of space and time would collapse into oblivion. Imagine if a person was standing at the edge of the event horizon, looking out into the universe, they would see future events unfolding at an incredibly fast pace, like watching a movie in fast forward. Centuries, millennia, even the entire cosmos would seem to change in the blink of an eye. This is the point where time and reality bend, where science becomes more unbelievable than fiction. In the 1930s, when Robert Oppenheimer calculated these processes, he concluded that the formation of black holes was indeed possible. But he made a crucial mistake. He assumed that black holes would always remain invisible. He believed they would be too small and dark to ever be seen against the blackness of space. However, had he consulted astronomers, he would have known that most stars in the universe do not exist alone. Instead, they exist in binary systems locked in a gravitational dance with a companion star. And this very fact became the key to discovering black holes. In 1971, a young astronomer, Paul Mourden, found the first real evidence of a black hole. Working at the Royal Greenwich Observatory, he adopted an entirely new approach. If a star was emitting X-rays, it signaled something extraordinary. X-rays can only be produced in extreme conditions where the laws of physics are pushed to their limits. Paul Mourden soon realized that he had found something highly unusual. A star being influenced by an invisible force signaling with its radiation that a hidden monster was lurking nearby. This was the first time science tried to capture the shadow of a black hole, and thus began the pursuit to uncover the darkest mysteries of the universe. The 1960s were an exhilarating time for science. This was the era when humanity first set foot in space, and at the same time, the race to discover the most mysterious objects in the cosmos had begun. Scientists knew that powerful cosmic forces were at play, forces that could not be observed from Earth, especially X-ray radiation, which gets absorbed by Earth's atmosphere. This meant that if we wanted to see the hidden cosmic mysteries, we had to look beyond Earth into space itself. And so, for the first time, an X-ray telescope was launched into space. When scientists began observing the universe in X-rays, they discovered an entirely new and mysterious world. They saw that several unknown sources in space were emitting intense X-ray radiation. However, the telescope technology of that time was not advanced enough to precisely determine the locations of these sources. So, these sources were named after the constellations in which they were found. But the real mystery unfolded when scientists noticed that some X-ray sources were not alone, they were actually present in binary star systems. This meant that a visible star had an invisible companion, one that was extremely dense, and was emitting such intense energy that it did not match any known stars. This raised the question, could this invisible companion actually be a black hole? This discovery marked a turning point in the history of astronomy. In 1971, a young astronomer, Paul Mourden, made history when he accurately identified a black hole for the first time. This black hole became famous as Cygnus X1, the first confirmed black hole. Now, it was clear, black holes were not just mathematical concepts, they were real objects existing in the cosmos, defying the very laws of space and time. This discovery was not just a milestone for astronomy, but a new beginning for humanity. The mystery of black holes, which had remained unsolved for centuries, was now within the grasp of science. In the early 1970s, NASA launched its first X-ray satellite, Uhuru, which, from above Earth's atmosphere, detected hundreds of new X-ray sources. Now, scientists had clear evidence that something strange was happening in the universe. Some mysterious objects were emitting extremely high-energy radiation. But the real question remained, where was this energy coming from? Paul Mourden analyzed Uhuru's data and found that the location of Cygnus X1, an X-ray source, was now more precisely determined than ever before. But the biggest mystery was that this source was located near a highly luminous blue supergiant star, which was 30 to 40 times more massive than the Sun and 100,000 times brighter. Its surface temperature was between 30,000 and 40,000 degrees Celsius. But even this was not enough to produce X-rays. So, where were the X-rays coming from? Now, science had only one possible answer. This blue supergiant star had an invisible companion that was pulling its matter away. When a star is bound to an invisible force, it does not realize it immediately, but slowly starts losing its energy. And when matter spirals around a black hole before falling in, it can heat up to millions of degrees and emit intense X-ray radiation. This was the very signal scientists were trying to detect. Cygnus X1 was no longer just a name, it was humanity's first glimpse into one of the greatest cosmic enigmas. And at that moment, for the first time, humanity accepted the existence of Beale. The mystery of Cygnus X1 was deepening. For Paul Moorthen, it was like a puzzle, a star under the influence of an invisible force, yet that force itself could not be seen. It was like a shadowy predator, present, but invisible. This question might have remained unsolved for Moorthen had his colleague Louise Webster not deciphered the mystery. Louise Webster was working on stellar motion, and she had a new way of understanding these phenomena, the Doppler effect. When a star moves toward us, its light shifts toward blue, and when it moves away, its light shifts toward red. But when she analyzed the spectrum of the supergiant star, she noticed something unusual. This star was orbiting around something extremely massive but invisible. Something that was there, but could not be seen. Using the 100-inch giant telescope, she measured its mass and discovered that this invisible companion weighed 3 to 4 times the mass of the Sunday. It was too heavy to be a neutron star. So, what was it? The answer was clear. For the first time, scientists had solid evidence that this could truly be a black hole. In 1971, Paul Moorthen and Louise Webster published their discovery and officially announced that Cygnus X1 was indeed a black hole. This was a historic moment. For the first time, a black hole was not just a mathematical concept, but a real cosmic object. It was now undeniable. Black holes exist, they are real, and they are among the most bizarre and powerful entities in the universe. But this was just the beginning. Scientists continued their studies of these mysterious giants with even more advanced tools. Then came another revolutionary discovery. In 2015, for the first time, humanity felt the vibrations of the universe itself. LIGO, Laser Interferometer Gravitational Wave Observatory, was an extraordinary experiment consisting of 2 4-kilometer long laser beam observatories, one in Livingstone, Louisiana, and the other in Washington state. On 14 September 2015, for the first time, these detectors picked up something extraordinary, an invisible tremor originating from the depths of the cosmos. This was no ordinary event. It was caused by the collision of 2 black holes. This discovery was extraordinary. In 1916, Einstein had predicted gravitational waves. He stated that when massive objects move through space-time, they create ripples, much like a pebble thrown into water creates waves. But this was just a theory. No one had ever observed it until now. 100 years later, this prediction had finally been proven true. LIGO's discovery fully confirmed the existence of black holes. They were no longer just a game of cosmic calculations. They were real cosmic events that could shake space and time itself. It was now proven that black holes were not just dark, hidden monsters. They were alive, they were shaping the universe, and they were bending space-time with their gravitational waves. But behind this great discovery lay another untold story, Louise Webster, whose name was almost erased from the history of science. Her discovery changed the way we understand the universe, yet she never received the recognition she deserved. On the other hand, Paul Moorthen, who helped uncover Cygnus X1, used the money from his discovery to buy his first property. This journey was astonishing. It began with mathematical equations, passed through X-ray astronomy, the Doppler effect, and ultimately led to LIGO. On 14 September 2015, when LIGO's detectors measured gravitational waves, it was a sign of 2 massive black holes merging together. This was a cosmic dance, a dance in which 2 colossal black holes spiraled toward each other, embracing until they became one. And the ripples from this dance spread across space-time itself. For the first time, we had felt one of the deepest mysteries of the universe. Those ripples, created billions of light-years away by 2 colliding black holes, had reached Earth. It was proof that we could now understand the universe not just through sight, but by listening to its heartbeat. Black holes were no longer just a part of imagination. They had become our reality. Imagine 1 billion years ago. Back then, life on Earth existed in its simplest form, perhaps just single-celled organisms drifting through the oceans. But at the same time, in a distant part of the universe, two colossal black holes were locked in a gravitational embrace. This was a cosmic dance, a gravitational waltz, where two immensely powerful entities spiraled around each other, slowly drawing closer. As they moved toward each other, their immense gravity warped space-time itself. Before they collided, an invisible tsunami spread across the universe, a gravitational wave traveling at the speed of light, racing outward in every direction. These ripples, this cosmic disturbance, traveled through space for billions of years, slowly stretching and fading, but never disappearing. And then, a special moment arrived, when this wave finally reached Earth. By then, our world had completely changed. Now, humans existed. And by sheer coincidence, these very humans had been preparing to detect the very ripples that the universe had sent a billion years ago. LIGO's detectors stood ready, waiting to capture that invisible pulse, an echo from the depths of time and space. We have seen the destructive power of a hydrogen bomb. A mere kilogram of matter can be converted into energy and cause massive devastation. But when these two black holes merged, 3 times the mass of our Sun vanished in an instant, completely transforming into gravitational waves. This event was so powerful that, for a brief moment, it released 50 times more energy than all the stars in the universe combined. Had this energy been released as light instead of gravitational waves, it would have shone 50 times brighter than the entire universe itself. This was the most violent and energetic event ever witnessed. But the discovery of black holes did not start here. It had begun much earlier, even before the discovery of Cygnus X1 in 1971. In the 1950s, astronomers developed a new tool, the radio telescope. This was the first time humanity had attempted to capture the invisible waves coming from the cosmos. At that time, no one expected that stars could emit radio waves. Most known stars only emitted heat and visible light, thermal radiation, also called black body radiation. But radio waves have a wavelength 1,000,000 times longer than visible light, and according to scientific theories of the time, it was impossible for stars to emit radio waves. But then, the universe revealed yet another mystery. Scientists began detecting several mysterious radio signals from space. These signals shocked everyone. Where were they coming from? Who or what was sending them? Was it a signal from an alien civilization on some distant planet? Or was it a natural cosmic phenomenon from the farthest reaches of the universe? The problem was that radio waves are incredibly long, making the images from radio telescopes blurry and difficult to interpret. It was like trying to see through thick, foggy glass. Scientists could not precisely determine the location of these signals. But one thing was certain, something the universe was sending signals beyond our understanding, and these signals marked the beginning of a new cosmic mystery. In Cambridge, scientists detected a mysterious signal, a radio source named 3C273. It was a strange and enigmatic signal, but no one knew exactly where it was coming from. It was located somewhere in deep space. But what was it? Was it a star? A galaxy? Or something else entirely? Then, an extraordinary event was about to unfold. The moon was about to cover this radio source. The motion and position of the moon were precisely known to science. This presented a golden opportunity for astronomers. If they could observe when 3C273 disappeared and when it reappeared, they could determine its exact location. When they performed the calculations and searched for this source using photographic plates, they found that there was indeed a star. But this was no ordinary star. It was a mysterious object from which a massive jet was emerging, a structure never seen before in any star. To unravel this mystery, Australian astronomer John Bolton used the Perkins radio telescope. This was a state-of-the-art instrument capable of detecting radio waves from deep space. But this time, it wasn't a regular signal. It was something extraordinary. Bolton wrote to his colleague, Martin Schmidt, we have pinpointed its exact location. Can you obtain its spectrum? For astronomers, analyzing an object spectrum is extremely important. By splitting light into its various colors, scientists can determine which elements make up the object. Every element, hydrogen, helium, calcium, carbon, produces unique absorption lines. These act as a chemical fingerprint, allowing scientists to understand its composition and even its motion. But when scientists studied the spectrum of 3C273, the results were unbelievable. This was no ordinary star. It was one of the most mysterious and powerful objects in the universe, a quasar. This discovery marked a revolutionary turning point in astronomy. For the first time, humanity realized that there were forces in the universe far beyond our imagination. 3C273 showed us that some objects could be so powerful that they could emit more energy than an entire galaxy. This was the first solid evidence of supermassive black holes, one of the most enigmatic entities in the cosmos. This breakthrough pushed the limits of our understanding and proved that we are still merely scratching the surface of the universe's greatest mysteries. It was a cold night in December 1962 when Martin Schmidt stood on the verge of a revolutionary discovery in the history of astronomy. He had arrived at the Mount Palomar Observatory in California, home to the world's largest optical telescope, the 5-meter-wide Palomar telescope. His goal was to obtain the spectrum of a mysterious radio source named 3C273, which had remained an unsolved enigma until now. Schmidt was a seasoned astronomer, accustomed to observing distant, faint galaxies and stars. But this time, something strange happened. He pointed his telescope toward 3C273, collected the light, and recorded its image on a photographic plate. But when the plate was developed, something was wrong. The entire image was blurred. 3C273 was extraordinarily bright, so intense that the plate could not handle its intensity. It was far more powerful than he had anticipated. He observed it again, this time more carefully, and succeeded. But when he examined the spectrum of 3C273, a new mystery unfolded. It did not match the spectrum of any known star or galaxy. He took it back to Caltech, showed it to his colleagues, but no one could understand it. What was this object? Why was it so bright? How was it emitting so much energy? Soon after, John Bolton wrote to Schmidt, suggesting that he publish a paper in Nature to confirm the position of 3C273. But Schmidt was puzzled. What could he write about an object he didn't fully understand? One afternoon, after having lunch, he returned to his desk. He stared at 3C273's spectrum once again. And then, it struck him, a pattern. There were dark lines in the spectrum, but they were strangely shifted toward longer red wavelengths, as if someone had stretched them across the entire spectrum. Schmidt immediately compared this with the most familiar spectrum in astronomy, the Balmer spectrum. This spectrum represents the emission lines of hydrogen atoms, and since hydrogen is the most common element in the universe, it could be found in almost every celestial object. He placed the Balmer spectrum over 3C273 spectrum and saw something astonishing. They matched. But there was one shocking detail. The entire spectrum was redshifted. Redshift meant that this object was moving away from us at an extreme velocity. The faster an object moves away from us, the more its light shifts toward the red end of the spectrum. But 3C273's redshift was so extreme that it was moving away at 16% the speed of light. This was no ordinary star. Schmidt realized he was on the verge of something incredible. 3C273 was not an ordinary star, nor was it part of any normal galaxy. It was a quasar, the active nucleus of a highly distant galaxy, powered by a supermassive black hole. This black hole was devouring matter around it, generating tremendous energy, making it so bright that it could outshine entire galaxies. This discovery was a revolutionary turning point in astronomy. For the first time, scientists realized that the universe could harbor objects so powerful that they alone could outshine an entire galaxy. 3C273 was not just a quasar, it was humanity's first glimpse into one of the most mysterious entities of the cosmos, the supermassive black hole. A new chapter had been added to the history of astronomy. 3C273, the first discovered quasar. This was the moment when humanity had its first look at one of the brightest, most enigmatic, and most powerful objects in the universe. For scientists, this was unbelievable. 3C273 was billions of light years away, yet it was 100 times more luminous than normal galaxies. It was as if a single lamp was shining brighter than an entire city. But the most mysterious aspect was its size. It was not enormous, but relatively small. Its extent was only a few light days or light weeks across. The question arose, how could such a small object generate such immense energy? There was only one possible answer, a black hole. Humans had discovered the first evidence of an expanding universe in 1929, when Edwin Hubble found that the farther a galaxy was, the faster it was moving away. This meant that the universe was continuously expanding. If we rewound time, it suggested that 14 billion years ago, the entire universe originated from a single point, a massive explosion, known today as the Big Bang. But 3C273 added a new twist to this theory. It became clear that some objects were so energetic that they could emit more light than an entire galaxy. For the first time, scientists realized that supermassive black holes existed, cosmic giants that could generate incredible amounts of energy. As the discovery of 3C273 progressed, astronomers found more quasars, and it became clear that all these incredibly distant and powerful objects were powered by black holes. Initially, scientists thought that black holes were just mysterious objects lurking in the corners of the universe with no significant role in cosmic evolution. After all, only 1% of galaxies were active, meaning their supermassive black holes were producing detectable energy. This led to the assumption that black holes might not play a crucial role in shaping the universe. But this assumption was about to change. 3C273 proved that these dark cosmic giants were not just hidden entities, they were actually the most powerful objects in the cosmos, capable of illuminating entire galaxies with their energy. Black holes were no longer just symbols of destruction, they were also centers of creation and power. But the biggest question still remained, was this phenomenon limited to just a few galaxies? Or did black holes play a crucial role in shaping the entire cosmos? 3C273 had opened the door to this mystery, but the journey to solving it was far from over. In 1990, humanity revolutionized its vision of the cosmos with the launch of the Hubble Space Telescope. This was not just another telescope, it was a new window, a gateway that would allow us to peer into the deepest secrets of the universe. But the mission was far from smooth. After its launch, scientists discovered a serious flaw in Hubble's optical system. Its primary mirror had a microscopic defect, causing all its images to appear blurry. It was as if someone had put on the wrong prescription glasses and saw the world in a perpetual hedge. Fixing this error cost NASA $800 million. But once Hubble was repaired, what it revealed shook the entire field of astronomy. There had always been one major problem in observing space from Earth, our atmosphere. When we look at stars and galaxies from the ground, it's like trying to see a ceiling light from the bottom of a swimming pool. The rippling water distorts the light and makes it blurry, just as Earth's atmosphere distorts and blurs the image of distant stars and galaxies. But Hubble eliminated this problem entirely, because it was above the atmosphere. Now, for the first time, we could see the universe exactly as it was, sharp, radiant, and breathtaking. When Hubble gazed deep into the centers of nearby galaxies, scientists made a shocking discovery. Stars at the galactic cores were spinning at unimaginable speeds. Their velocities were so extreme that if there wasn't some unseen force holding them back, they should have been flung off into space, escaping the galaxy's gravity. But they weren't. There was only one possible explanation: an invisible, unimaginably dense, and incredibly massive object was anchoring them in place. Every galaxy had a supermassive black hole at its center. This was a groundbreaking revelation. The question was no longer whether black holes existed. The question now was, if every galaxy had a supermassive black hole, were only 1% of them active? What were the other 99% doing? The answer was as simple as it was astonishing. Only those black holes that had enough food were active. Black holes surrounded by gas, dust, and fragmented stars consumed these materials, generating immense energy and appearing as brilliant quasars. But black holes with nothing to feed on became dormant, silent, invisible, and completely inactive. Now, the truth was clear. Black holes weren't just lurking monsters hidden in the universe's corners. They were everywhere, playing a vital role in shaping the cosmos. But the real question still remained: were black holes merely passive objects, or were they actually controlling the very fabric of our universe? Can black holes really influence galaxies? Initially, scientists believed that these cosmic giants had only a limited impact. As massive as they were also surprisingly small. Imagine a black hole with a mass of 1 billion suns, but its gravitational influence extended only a few dozen light years. Meanwhile, an entire galaxy could stretch 20,000 to 30,000 light years across. It seemed that these celestial titans were isolated, confined to their own realms, disconnected from the rest of the galaxy. But then, a mystery unraveled. Scientists realized that black holes were not just silent rulers of gravity, they had the power to shape entire galaxies. They could unleash powerful jets of energy that extended millions of light years into space. Gradually, it became clear that black holes were not merely an end, they were actively involved in the birth and evolution of galaxies. The biggest proof of this was 3C273. 3C273 was not an ordinary star. It was the first quasar ever discovered, the blazing heart of a supermassive black hole, where matter swirled around at incredible speeds, heated up, and became one of the brightest sources of light in the universe. But this was no ordinary black hole. It was more massive than 1 billion suns. It was 100 times brighter than its entire galaxy, and its light was spreading across the cosmos. Quasars, or quasi-stellar objects, are actually the active centers of galaxies. Most of their energy does not come from stars, but from matter falling into the gravitational pull of a black hole. As gas and other materials spiral inward, they heat up intensely, emitting radiation, making quasars some of the most luminous objects in the universe. Earlier, scientists believed that black holes played no significant role in the cosmos. After all, only 1% of galaxies were classified as active, meaning their central black holes were actively emitting energy. This led to the assumption that most black holes were dormant, inactive, and inconsequential. But then, this perception completely changed. We now began to understand that black holes were not just hidden destroyers, they were architects of the cosmos. They shaped galaxies, controlled the rate at which stars formed, and spread energy across the universe. Black holes were no longer just a place where everything ended. They had become a symbol of a new cosmic balance. The cosmic titans, the influence of black holes still echoes through the universe. When you gaze at the night sky, admiring the twinkling stars, have you ever wondered if something invisible yet immensely powerful is lurking among them? A cosmic titan capable of devouring time, light, and matter, something from which nothing can escape once it crosses its threshold. This is the story of black holes, the most mysterious and powerful entities in the universe. Every star that twinkles in the sky is not eternal. When a massive star reaches the end of its life cycle, its fuel depletes. Gravity starts pulling it inward, causing it to collapse. If the star is small, it may become a white dwarf. If it's slightly larger, it could turn into a neutron star. But if the star is immensely massive, it collapses under its own weight, giving birth to a black hole. At this moment, the star's contraction becomes unstoppable until it collapses into itself, reaching a singular point known as a singularity. Here, the laws of physics break down. There is no time, no space, just an abyss of the unknown. In 1963, astronomer Martin Schmidt observed an object so luminous that it outshone an entire galaxy. But this was no ordinary star. It was the first discovered quasar. When scientists analyzed its light, they found that this object was billions of light years away, yet it was 100 times brighter than typical galaxies. There was only one possible explanation. At its core lay a supermassive black hole, devouring surrounding matter and releasing enormous amounts of energy. In 1990, NASA launched the Hubble Space Telescope into space. Since it was positioned above Earth's atmosphere, it could observe the universe with unprecedented clarity. When it turned its gaze toward galaxies, astronomers made an astonishing discovery. At the heart of every galaxy, there existed a supermassive black hole. But the question remained, how do black holes influence their galaxies? Initially, scientists believed that black holes were too small to have a significant impact, with their influence limited to just a few light years. However, they soon discovered that black holes could control galaxies not just through gravity, but also through powerful jets of energy. In the 1950s, astronomers detected a mysterious signal. Some galaxies were emitting intense radio waves. When they examined it closely, they found that these signals were coming from a galaxy known as Cygnus A. But the signal appeared to be originating from two massive lobes, one on the right side of the galaxy and one on the left. The mystery remained unsolved until the Very Large Array (VLA) telescope focused on it. What they discovered was breathtaking. Enormous jets of energy were erupting from the center of Cygnus A, stretching millions of light years into space. One jet was coming toward us and appeared brighter due to the Doppler effect. The other jet was moving in the opposite direction, making it appear dimmer. These jets were so powerful that they shook the entire galaxy's atmosphere, proving that black holes don't just consume matter, they also reshape the very structure of the universe. Now the question was, does our Milky Way galaxy also have a black hole at its center? The answer was yes. At the heart of our galaxy lies Sagittarius A*, a supermassive black hole located 27,000 light-years away from Earth. It has a mass 4.2 million times that of the Sun. It controls the orbits of countless stars in our galaxy. But it remains quiet as it currently lacks enough food to consume. If a massive gas cloud or a star ever falls under its gravitational pull, it could awaken again, igniting the heart of the Milky Way once more. There was a time when black holes were seen only as symbols of destruction, places where everything disappears forever. But now, we know that they don't just consume matter, they shape the entire cosmos. They help form new galaxies, regulate star formation, and maintain the cosmic balance of the universe. So the next time you gaze at the stars in the night sky, remember, hidden behind their glow, there may be an invisible giant, a black hole, one of the most mysterious forces in the universe. Black holes are not just lurking in the depths of darkness, they are writing the story of the entire cosmos. Imagine, standing at a place where light itself stands still, where time has no meaning, and where nothing can ever return once it has crossed the threshold. This is not science fiction. This is the world of black holes, the mysterious gateways of the universe, beyond which no one has ever dared to venture. But do you know that the journey to discovering them has been just as thrilling as the black holes themselves? Come, let us take you on a journey that begins with the death of stars and leads to the greatest mysteries of the cosmos. Every star you see shining in the night sky is not immortal. Deep within, a constant battle is raging. Gravity tries to collapse it inward, while the energy from its burning fuel pushes it outward. But when that fuel runs out, the battle ends, and the star surrenders to gravity. If the star is small, it becomes a white dwarf. If it is slightly larger, it turns into a neutron star. But if it is immensely massive, it keeps shrinking, collapsing under its own weight, until it vanishes into itself, and a black hole is born. A singularity, a point where all the laws of physics break down, where density becomes infinite, and where time and space cease to have any meaning. The existence of black holes had been theorized before, but they were officially named in 1967 by American scientist John Wheeler. Before this, scientists simply called them gravitationally collapsed stars. But the name black hole turned them into a mystery that everyone wanted to understand. Newton thought that gravity was an invisible force that held stars and planets together. But then came Einstein, and he completely changed this idea. He explained that gravity is not an invisible rope, but rather a curvature of space-time. Imagine placing a heavy ball on a fabric. The fabric bends downward. Now, imagine if the ball was so heavy that it tore a hole in the fabric. This is exactly what happens when a star collapses into a black hole. It doesn't just bend space, it swallows time itself. In the 1950s, astronomers detected mysterious radio waves from space. When they traced their source, they found that these signals were not coming from an ordinary star, but from an extremely small yet powerful object. What was it? In 1971, astronomer Paul Moorthen identified a black hole for the first time. This was not a normal star. It was located next to a blue supergiant and was emitting intense X-rays. But where were these X-rays coming from? The answer was a black hole. When matter falls into a black hole, it heats up to millions of degrees and emits X-rays. These X-rays were the first real evidence that black holes were not just a theoretical idea, but a cosmic reality. Even our own Milky Way galaxy had a hidden black hole at its center. But this black hole was quiet, dormant, and asleep. In the 2000s, to scientists, Andrea Gage and Reinhard Genzel began studying it closely. They discovered that stars around it were orbiting at extremely high speeds, so fast that if there wasn't an invisible force holding them, they would have been flung into space. When they calculated the mass of this unseen force, they found it was equal to 4 million suns. It was now clear. Almost every galaxy in the universe had a supermassive black hole at its center. But there was another way to detect black holes, by listening to their heartbeats. In 1916, Einstein had predicted that when two massive objects collide, they would create gravitational waves, ripples in space-time that spread across the universe. But the question was, how could we hear them? Two black holes, which had been orbiting each other for billions of years, suddenly merged, and the waves from this collision spread across the universe, eventually reaching our Earth, where our observatories detected them. Black holes are not just destroyers. They are also the architects of creation. They shape galaxies, give birth to stars, and maintain the balance of the cosmos. Without black holes, the universe might not exist in its present form. And perhaps, neither would we. What happens if someone falls into a black hole? To an outside observer, that person would never appear to cross the event horizon. But for the person falling in, time would slow down, stretching infinitely. And when they finally reach the singularity, what happens there? We still don't know. Imagine, you are standing at a place where time slows down, where light freezes in its tracks, and where, once you enter, nothing, not even you, can ever return. This is not science fiction, but the world of black holes, the mysterious gateways of the universe, beyond which no one has ever dared to venture. But did you know that their discovery has been an incredible adventure? It all began a billion years ago, when Earth had only the most primitive life forms, and somewhere in the universe, two colossal black holes were engaged in a deadly cosmic dance. A collision that shook the universe. 1 billion years ago, in a distant corner of space, two monstrous black holes were locked in their final embrace. They spiraled closer and closer, until finally, as they merged into one, they sent a massive tsunami of gravitational waves rippling across space-time, traveling at the speed of light, spreading throughout the universe. In that single moment, 3 times the mass of the Sun was converted entirely into pure energy, a release so powerful that it outshone the entire Milky Way galaxy by a factor of 50. But the mystery of black holes doesn't end there. The discovery of quasars. In 1963, astronomer Martin Schmidt observed a mysterious glowing object. But this was no ordinary star. It was a quasar, the brightest object in the universe, fueled by the unimaginable power of a supermassive black hole. Scientists realized that quasars exist in galaxies where black holes are actively feeding, consuming matter, and emitting immense amounts of energy. But this also meant one thing: every galaxy in the universe might have a supermassive black hole at its center, the heart of every galaxy. In 1990, NASA launched the Hubble Space Telescope, a groundbreaking instrument that could peer beyond Earth's atmosphere into the depths of space. When Hubble turned its gaze toward the centers of galaxies, scientists were shocked. Every galaxy had a supermassive black hole at its core. But if black holes were present at the center of every galaxy, why were only 1% of them active? The answer was simple: only those black holes that had enough food, such as gas clouds and fragmented stars, remained active and emitted immense energy. The hidden guardian of our galaxy. Our Milky Way galaxy also harbors a supermassive black hole at its core, Sagittarius A star. Asterisk, it is located 27,000 light-years away from Earth. Asterisk, it has a mass of 4.2 million solar masses. Asterisk, in 2020, scientists confirmed its existence by tracking the rapid motion of nearby stars, proving that something incredibly massive was lurking there. But here lies a crucial mystery. Why is our black hole so small? Other quasar black holes can range between 10 to 60 billion solar masses, yet Sagittarius A asterisk is only 4.2 million solar masses. If our black hole had been much larger, it would have produced powerful jets that could have blown away the gas from the galaxy, the very gas responsible for star formation. Had this gas been ejected, our galaxy would have formed only one generation of stars, and after that, no new stars would have been born. And perhaps our Sun would never have existed. So, was it just a coincidence that our black hole was smaller? Or was this the reason we exist today? Capturing the shadow of a black hole. In 2019, the Event Horizon Telescope captured the first ever image of a black hole. It was located at the heart of the M87 galaxy and had a staggering mass of 6.5 billion solar masses. This historic image revealed a dark region, the shadow of the black hole. Recent discoveries about black holes. Recently, astronomers have made some groundbreaking discoveries related to black holes that are reshaping our understanding of the universe. The more we explore, the deeper the mystery becomes. Imagine, in the infinite corners of the universe, where even light loses its way, there exist forces beyond our understanding. Every time science peers into this darkness, a new mystery unfolds. Recently, astronomers have made some shocking revelations about those enigmatic titans of the cosmos, black holes. NASA's James Webb Space Telescope, JWST, has detected a supermassive black hole that came into existence just 800 million years after the Big Bang. This black hole powers a quasar and has a mass 1 billion times that of our Sun. This discovery challenges everything we thought we knew. Did black holes exist before galaxies? Were they, in fact, the first architects of the universe? 12.9 billion light-years away, another black hole has made its presence known. Scientists have named it Blazar J041000139. Its power is so immense that it warps space-time around it. With a mass equivalent to 700 million suns, This is one of the most powerful blazars ever discovered. Its brilliance and energy make it one of the most extreme astrophysical phenomena in the universe. Until now, we believed that dark energy, which accelerates the expansion of the universe, originated from an unknown source. But two recent studies have shaken this belief. Scientists now suspect that black holes themselves could be the source of dark energy. If this theory proves true, it would be one of the greatest breakthroughs in the history of cosmology. The mysteries of the universe are as terrifying as they are exhilarating. When we gaze into the dark night sky, the twinkling stars remind us that somewhere in this infinite abyss, black holes are shaping space and time, molding the universe itself. But the biggest question remains unanswered: are black holes merely destroyers? Or do they hold the key to some deeper cosmic secret? Black holes are not just symbols of darkness and destruction. They're the architects of the cosmos. They sculpt galaxies. They control the birth and death of stars. And perhaps they played a role in our own existence. So, the next time you look up at the night sky, remember, perhaps we exist because a distant black hole shaped our galaxy into what it is today. If you found this journey fascinating, like, share, and subscribe to the channel. Electric light bulb, what are your thoughts? Could there be another universe beyond a black hole? Or is there only nothingness? Let us know in the comments. We'll meet again on another journey, uncovering new mysteries. The universe is infinite, and our search has only just begun.